DFT. I'm going to talk about DFT in the canonical ensemble. Um, Sometimes at these meetings, I've started off talks by showing clips of the titles of papers in famous journals, Nature and Science, and all this. I'm not going to do that today. I'm also not here to correct anything or to make some important observation. I'm really just did this maybe because of sitting at home and working from home all the time and getting bored. But I really, at some point, just wanted to understand in a sort of simple pedestrian way why we always do DFT in the grand canonical ensemble and not the canonical ensemble. So, I mean, we all know the basic reasons. I mean, one thing is, if you've ever seen the proofs that underlie DFT, then you know that they're always formulated in the grand canonical ensemble. It's also, of course, if you think about it for just a moment, it's easier to do functional derivatives in the grand canonical ensemble because there's no constraint on the density. So the density can vary freely. In the canonical, of course, you always have to have a constraint that the number of particles is fixed. And the last reason is, what? Start my video, sorry. The last reason is that there are several exact results which are known for the grand canonical ensemble, particularly the most famous one, besides the ideal gas, is the hard spheres in one dimension, or hard rods, for which there's an exact general solution due to Perkis in the 70s. And in fact, that was extended to mixtures and to sticky hard rods. All of these are known exactly and have played an important role in developing models in DFT. So given all those good things, the question is, why care about doing DFT in the canonical ensemble? And of course, one reason is if you're not a sort of DFT expert or theorist, and you're not a condensed matter theorist, most people are much more comfortable working at fixed particle number, or thinking at fixed particle number, than they are at of open systems. And so often people don't mind if you have fixed volume or fixed pressure, but the grand canonical ensemble somehow seems unnatural. Another reason is because of dynamics, dynamical density functional theory, power functional theory. Everything in dynamics and statistical mechanics, starting from the Liouville equation on down, is formulated for a fixed number of particles. And so we often want to use these sophisticated functionals developed in DFT in order to input into some dynamical models. And there's always a question of whether this is really a good idea, because the models are, the functionals are developed for the grand canonical ensemble, the models are canonical, the dynamics are canonical. And so that's always a weak point of this kind of approximation. I noted here that everyone, I think, who's thought about it at all sort of knows that it's possible to do DFT in the canonical ensemble. And just as I've always known this. And so maybe like me, other people wonder why we don't actually see it. And the last thing I put is because doing it in the canonical ensemble would justify about 1 million papers where people minimize the free energy at constant n and call it density functional theory, even though there's no real theoretical basis for what they're doing. So that's the motivation for wasting a lot of time looking at this. But I hope the results, I was a little bit surprised by the results, and I hope that you'll be, if not surprised, at least amused at some of the things which I've seen. So the first part of this talk, I'm going to talk. I want to go back through some of the formalism. I'm not going to prove the entire theorem. It's not that it's that difficult, but just because I don't have the time. But I'm just going to go through the first part where you establish a connection between fields and local densities. I'm sure that all of you know that the first principle of density functional theory is that there is basically a one-to-one correspondence between applied external one-body fields and the local density that results from in equilibrium. I'm quite aware that, so I'm going to take a very pedestrian view, the oldest view based on looking at partition functions. I'm aware, of course, that there's more sexy things by looking at the convexity properties of the free energy or doing constrained search. But I prefer this route in a way because this is the only way that you can really talk about exact models. And so I prefer to ground myself in the machinery which I'm going to use to actually do calculations. So to start at the beginning, let me see. I don't know. Can somebody tell me, are you able to see my cursor?
Yes, we see the cursor.
Excellent. Yeah. So to begin in the beginning, I'm going to go through this little argument, and in each equation, I'm going to have two lines. One is the statement for the canonical ensemble, and the second one is the statement for the grand canonical ensemble, the statement that we normally see. So to begin with, I'm going to define some distribution functions or state the distribution functions. So this is the usual canonical distribution function with the Hamiltonian here. These usual factors, the combinatorial factors and Planck's constant in front, and the partition function, which I've written out down here. And this is the equivalent for the grand canonical ensemble. And the only difference is that we have the chemical potential in this expression, and we have the grand canonical partition function. And that's written here. And so these can both, you could write them in the same way by replacing the integrals by a trace. And here the trace would just include the sum over particle number as well. And of course, from these things, we have the free energies, which are equal to minus the log of the partition functions. The last bit of notation is this is the local density operator, which is a distribution, in fact, mathematically. So this is just a sum of delta functions with the position r at the localized at each particle. And I'm using a notation here. Maybe I used it in the previous slide, not yet. I'm using it here, which I've started using just because I find it more convenient, where I include the spatial argument as a subscript rather than as an argument written in the usual way, like this with brackets. So this is the phase function, and the local density is just its average. So we just have to multiply it by the distribution function and integrate. And in the grand canonical case, we have to also, of course, do the sum over particle number. So this is the explicit expression for the local density. And of course, everyone sees this immediately, but just to point it out, just so that we have this fact handy, by definition or by construction, there is only one local density for each field. So that, of course, is part of the eventual two-way implication that we want to prove. And I also remind you, because it's useful and it will be used a lot, that the Hamiltonian is, of course, linear in the external field. And in fact, you can write it in this form, an integral over this phase function times phi of r dr, because this just gives you the sum of the one-body potential evaluated at each particle position. So now begins the real argument. Following Merman, as far as I know, you introduce a functional of two fields, which is defined like this. And so the sort of meaty term has two different distribution functions, one based on phi and one based on phi naught. And you have this additional constant term out here, which is important, but it's, yes, it's just a constant. And you have the equivalent thing in the grand canonical ensemble, where the only difference is we have the sum over particle number as well. And then we invoke the Gibbs inequality, which I think is really Jensen's inequality, but anyways, which is in this context often called the Gibbs inequality, which says the sum over I from 1 to n of the probability of state I times the logarithm of the probability of state I divided by some other probability of the state I. This whole thing is always greater than or equal to 0. And importantly, it's only equal to zero. It's equal to zero if and only if all of the state probabilities are the same. So here we have two distributions, PI and QI, and we're just comparing them. This is like the Leibler-Kovac function, or the relative entropy between the two distributions. So this kind of thing is used a lot in statistical mechanics. So what this tells us, we can apply this to our expression, because we have basically the same thing here, except instead of summing, we're doing an integral over all points in space. You could think of discretizing the system, and then this would apply exactly. In the continuous version, you should always have in mind that these statements are true up to a set of measure 0. But in any case, this has the right form, the same form as we have here. And so we can use this Gibson equality to say that this thing is greater than or equal to this constant term, A of A naught or omega of phi naught, with the equality only if the two distributions are the same. Before getting into that, I just note that there's another way to write these functionals, and that is by putting in the actual definitions of these distribution functions and canceling some terms and doing some uninteresting integrals. We end up with an expression like this, where here the A of phi naught has been replaced by A of phi, and the same thing for omega. And this complicated expression just reduces down to something involving the two external fields. And that just has to do with the fact that the Hamiltonians otherwise are the same, and all of the terms cancel out. So this is another statement. This is equivalent to this form of this statement. So this is what I just mentioned. And then we go through, we do the same thing again, but we exchange the two fields. So we get exactly the same expression with phi and phi naught, phi and phi naught interchanged. We add these together, and you see we get A of phi plus A of phi naught. Here we have A of phi naught plus A of phi, so these things cancel. And we just get that this remaining thing is greater than or equal to 0. Now, each of these expressions was the sum of two things which are greater than or equal to 0. So this whole thing can only be 0 if both of them are individually equal to 0. And by the Gibson equality, that means that the distributions have to be the same. Now, what does this mean to say that the distributions are the same? Well, it means, for example, that the ratio of the distributions is equal to 1, no matter what the coordinates of all the particles are, what their momenta and their positions are. And the same thing in the grand canonical ensemble. And so if you write out this expression and move some terms around, you get something like this. Obviously all of the kinetic stuff cancels out, and you just get, again, this term involving the two fields. And you can, if you write it in this way, you say this is equal to something which is basically the ratio of the partition functions, or it's exactly the ratio of the partition functions. But the point here is that this thing on the left depends on all of the particle coordinates, and the thing on the right doesn't. And this has to hold true no matter what these coordinates are. So the only way that can be the case is if the difference between these two functions, phi and phi naught, is a constant. And this is true in both the canonical and grand canonical case. So the only way this inequality that we were looking at is saturated is if the two fields are related by a constant. Now, if you put this in and see and simplify the resulting expressions, in the canonical case, you just get an identity. And so it's true no matter what the constant C is. In the grand canonical case, you don't. In the grand canonical case, on the left-hand side, you get e to the minus beta nc, that's just this term. But here you get something complicated because the C basically shifts the chemical potential, and then you're summing over all the particle numbers. And it's easy to show that these things cannot be equal in general unless C is equal to 0. So in the canonical case, this constant is arbitrary. In the grand canonical case, it has to be 0 in order to saturate this inequality. So this is, to use a fancy phrase, this is a kind of gauge symmetry in the problem where in the canonical case, and you can just see this in the statistical mechanics, you can shift the potential by a constant and nothing changes. But that's not true in the grand canonical ensemble because it has the effect of changing the chemical potential. So this is the only difference between the two ensembles thus far in the argument. And if you then continue, from this, what you learn is that either the fields are related in the canonical case by a constant, or in the grand canonical case, they're identical. Either that, or this term, this factor, this functional has to be greater than 0. If the integrals are greater than 0, then their arguments must be non-zero, of course, at least up to a set of measure 0. And so that means that these fields, these densities cannot be the same at all points. So either these external fields are related in a simple way, or the densities cannot be equal at all points. And that statement can be turned around, and you can say the densities are, if the densities are equal, that implies that the fields are related in this way. That is, that they're the same in the grand canonical ensemble, or they're related by a constant in the canonical ensemble. And given the reverse statement, which I already said, namely that each field implies a particular density, this establishes a relation, a bijection between the densities and the fields. There's a question of, which some of you will know, maybe some of you don't, of what's called the representability of densities by fields. I don't want to get into it as a technicality, but for those who are experts, it's easy to work your way around this problem. You just restrict the domain that you're functions that you're looking at. But anyways, to keep things simple, so what this is saying is, in the grand canonical ensemble, we have the usual statement, which you probably all know, that every density is that in some sense that can be used is generated by some external potential, and every external potential generates some unique density. In the canonical case, almost the same thing is true. You just have to replace external field by family of external fields, related by, where the family is related by arbitrary constant. You can, I'm not sure if I said this on the next slide. Okay, you can even, I think I did. You can, let me go ahead and say it here. You can even get rid of this constant if you impose a gauge condition. And what do I mean by a gauge condition? This constant lets you fix something in the problem. You could fix, for example, the minimum value of the potential, and say I only look at potentials in which the minimum is 0. In that case, the constant is fixed, and you have this one-to-one relationship between densities and fields. You could look at something more sophisticated, because you might say, well, sometimes I have potentials that go to infinity, so I don't like to do that to talk about their value. So you could talk about the partition function. You could say, well, I only look at potentials such that the partition function is exactly equal to 1. That fixes this constant, and then essentially it reduces the domain of fields that you're looking at, and then the statement becomes exactly the same in the two ensembles. So in some sense, the difference between them is quite trivial at the formal level. And this is as far as I'm going to go. The rest of the arguments is exactly the same in the two ensembles. And so what you end up with is a conclusion that formally there's no real difference between doing DFT in the two ensembles. So I think I skipped somehow from part 1 to part 3, but anyways, okay, so I'm better at calculus than I am at counting. Anyways, given this, the question is, well, why don't we do it in the canonical ensemble? And the natural place to start is to look at some exact results. And how do you get exact results? Well, the strategy is, the only strategy I know is outlined on this slide. Some guy bets you, he'll buy you a drink if he can give you a potential and you can determine the density, the functional. And so what you do is first you construct the density for an arbitrary field, given whatever constraint you're imposing on your problem. and you calculate the partition function. Then you somehow invert this relationship where the field gives you the density to get the field as a function of the density, so that the density gives you the field. Yeah, I've written this backwards, I see. So what we know is this, and what we want to invert is to get this. So these should be interchanged. And then having done that, you can construct the Helmholtz functional, and this is part of the argument which I left out, but it's just equal to this general partition function minus this term, and then with all of the fields replaced by the field as the function of the density. This is the strategy. It's the same strategy in the canonical and grand canonical ensemble. And then here I note this thing which I mentioned on the previous slide, that you can always get rid of this constant floating around by imposing some sort of gauge condition. But in fact, this is not necessary, as you'll see in a minute. You can just live with the constant and it changes nothing. So to begin at the simplest case, the one that anybody who teaches this would give the students, let's do this for an ideal gas. So what do you have to do? You have to calculate the partition function, and this is what the partition function is for an ideal gas with an arbitrary field. Calculate the local density, and if you need to, you can get it from this by functional differentiation, or just write it down because we all know what it is, which looks like this. And of course, I'm working in the canonical ensemble. And I note here that you have this degeneracy. You can see that I can shift the potential by a constant, and the constant cancels in the numerator and denominator. That means that this expression cannot really be inverted. That is, I can't determine phi because there's not a unique phi for any given density. There's a family of them. So what I'm going to do is write this denominator, which is a constant, and I'm just going to call it C, basically the constant that we had floating around before. And now I invert this, which I can do if I don't care what C is, and I get beta phi is equal to beta C minus this logarithm of the density. And then I put it into my partition function, and I get this expression. And here you can see this, in fact, doesn't even depend on the density. It just depends on the constant C. The density comes in by these factors of n, the number of particles. And so this is what I was saying before. You could choose C so that this whole thing is equal to 1 if you insist on having a uniqueness, but there's no need to do that. Given these ingredients, you can then take the final step and form the Helmholtz functional, which is like this. And what you find is, lo and behold, the C's cancel out, and you just get an expression. And this expression looks a lot like the one from the grand canonical ensemble, which I've written here. I put a mu here, but there shouldn't be because it doesn't depend on mu, the chemical potential. But anyways, you can see there's a rho log rho term, which is the same as in the grand canonical ensemble. And then instead of having this rho of R, which would just integrate to give you the average number of particles, you have this expression, which is a constant. So this really changes nothing in terms of DFT, in terms of minimizing the functional. By the way, if you take the large n limit of this and use Stirling's approximation, this becomes exactly n that you have in the grand canonical ensemble. So in that case, that's an example of the two ensembles becoming the same in the thermodynamic limit. So that's a very simple example. There's another example, which I actually talked about last year in a different context, so nobody will be surprised that I would think of this. And that's small restricted geometries. So in these geometries, the idea is that you start off with a cavity, which is, let's say, spherical. And we're going to work with, let's imagine that there are hard particles, they're hard spheres. I don't care what the dimensionality is here. It could be 1 or 10 or anything else. And the idea is that these cavities are just a little bit bigger than the spheres. So that if the cavities overlap, I can't have a sphere in two cavities, two adjacent cavities, because if I put one in one cavity, and I try to put another in the other cavity, they would have to overlap. So I can only have an occupancy of 1, at least in adjacent cavities. And now for what I'm going to do, let me just set some notation because it will make everything a lot simpler. I'm going to define E sub I as the exponential of minus beta times the external field over one of these cavities. And n sub I is going to be the integral of the density over one of these cavities. So this will be the occupancy of one of these cavities, and this is the field the Boltzmann factor of the field integrated over one of these cavities. And so I'm going to look in particular right now in this talk at geometry, which is just chains like I've drawn here. This is a chain of two, and you can imagine extending this. So for a chain of two cavities, the partition function turns out to just be E1 plus E2. Notice I've taken into account the other factors in this definition. And the density has this simple form. And again, this is maybe some idiosyncratic notation. This is not a Dirac delta function. This is an indicator function, which is 1 if its argument is true. So it's 1 if the position is in the volume V1 and it's 0 otherwise. So I get one factor, which is basically for the, and this is talking, of course, about the center of this hard particle. So even though the cavities overlap, the center is always in one volume or the other. And in fact, when I talk about these integrals, I'm only talking about the accessible volume for the center of the sphere, not the entire cavity. So this is all well defined. What is V1 and what is V2, et cetera. So the density is just e to the minus beta 5r divided by the partition function, and then either in cavity 1 or in cavity 2. So again, this is easy to invert. In fact, in this case, you have e to the minus beta phi r is just this partition function multiplying the density. And I've written this all again here. And if you jump through the same hoops without even determining what these constants E1 and E2 are, well, you just get the ideal gas again. And that's no surprise because this is an ideal gas. There's no interaction between more than one particle. So it's just an ideal gas restricted to this volume. I went ahead and said this because this is not what you get in the grand canonical ensemble. The grand canonical ensemble is a little more complicated. So the result is that the Helmholtz functional is the ideal gas plus another term. And this other term has to do with the occupancy, say in cavity 1. And it's written like this. It's 5x and 1 minus x log 1 minus x plus x. And the origin of this term is particle number fluctuations. So in the canonical case, we have one particle, which is in either one of the cavities. So it's an ideal gas. But in the grand canonical case, we have fluctuations of particle number. And the fluctuations are cut off by the fact that I can't have 2 or more particles. And in fact, you have a kind of interference where if I have one particle here, then the fluctuation here I can only have 0. I can't even have a fluctuation up to 1. And so you get this kind of distortion of the ideal gas result due to these in some sense, virtual interactions between the cavities. So this is a little different, but not very different. The last example in this genre that I'm going to talk about is a chain of 4 cavities. And the reason I jumped to 4 is because this becomes more interesting. The reason is that imagine for a moment, first I have 3. Well, then in the canonical ensemble, if I have a particle here, I can't have a particle in the second one. So a second particle could only be in the 3rd cavity. And that's the only possibility to have 2 particles. So it's again, not a very interesting case. But if I have 4 cavities and 2 particles, I could have a particle in cavity 1 and a particle in cavity 3, a particle in 1 or a particle in 4. But notice that when one is in cavity 2, a particle is in cavity 2, the other one can only be in cavity 4. So suddenly things are a little bit more complicated. So, but it's easy to work out. So again, working the canonical ensemble, the partition function turns out to just be this product of these sort of Boltzmann factors. And the density is easy to write down, and it's easy to invert. And I've just written the expression here. So you get e to the minus beta 5r, and I've taken out the partition function. And it's, the density restricted to these volumes, and then with different weights according to which volume I'm looking at. And the weights have, again, to do with these Boltzmann factors. You can then form the Helmholtz functional, and you get something like this. And now what you see is that these constants are not canceling out. And remember, I'm only supposed to have one arbitrary constant, but even that I expect to cancel out. And so I can't stop here, as I did, for example, in the ideal gas. I need to actually determine what these constants are. And you can do that by integrating, say, this expression or the original expression for the density in terms of the field over each of the cavities individually. So if I integrate over the accessible volume of cavity 1, then I get the occupancy of cavity 1. And that's a functional of the density. That's something I can evaluate for any density. So that's a function of the density. And then that turns out to be equal to this. So I get a relation, when I do this for all 4 cavities, I get 4 equations. These are not independent because, for example, one particle always has to be in either cavity 1 or cavity 2. So that means that the occupancy of 1 plus cavity 1 plus cavity 2 has to be equal to 1. So these equations are not independent, but I do end up being able to solve for 2 of the constants, and 2 of them remain unknown. But as seems to always happen in these problems, the unknowns cancel out, and I'm left with an expression that involves only functionals of the density, something that is the ideal gas part here, and then these partial occupancies for each of the little cavities. Now you can do the same problem in the grand canonical ensemble, and I don't know of anybody who's done this, so I worked it out, and this is what I get. You can see that it's quite a similar functional. You have the same ideal gas part, of course, and then you get things which also involve the partial occupancies. They're different, and I can't say that there's any simple way I can go from one expression to the other, but obviously they're quite similar. Now you might think the canonical is special because I have this weird relationship between the occupancies, but you also have similar things in the grand canonical ensemble. For example, we're used to thinking in the grand canonical ensemble the density can be anything, but it can't really, because, for example, you can easily show that the occupancy of cavity 1 plus cavity 2 has to be less than or equal to 1, even though the whole system is capable of holding 2 particles. So you don't have a strict equality like this, but you still have constraints. And this really, it's a kind of simple manifestation of this V representability issue. Not any density that you can imagine can be expressed by some external field, because the ones that can be generated by an external field have to satisfy certain physical requirements. There's no physical density that doesn't obey these inequalities. So anyways, so far so good. And by the way, I can just tell you, having done both of these, this is actually easier in the canonical ensemble than the grand canonical ensemble. The equations are a little harder to solve in the grand canonical, basically because of the sum over particle numbers. Okay, the last problem I'm going to mention is the fun one. And this, I'll be honest with you, it took me months to work this out. For a long time, I thought it wasn't possible. I sort of beat my head against it. I wasted an enormous amount of time. I attribute all of this to COVID. I tried doing things like perturbative expansions and all kinds of silly things. And of course, as it always happens with these things, in the end, I realized that if I just looked at things from a slightly different angle, it was all quite simple, and I was incredibly stupid. Anyways, I'll show you what happens. So the only other important example of exact results that I know of are, as I mentioned at the beginning, hard rods or hard spheres in one dimension. And there's the famous result of Perkis that the Helmholtz functional is an ideal gas term. And now you're just integrating over one dimension. So these are just simple coordinates. Plus an excess term. And the excess term involves things that we all know and love from fundamental measure theory. These two sort of weighted densities, something that looks like a one-dimensional packing fraction, and something that looks like the scalar density of fundamental measure theory. And this is exact. This is an exact result that holds no matter what the external field is, including for infinite systems or finite systems or anything else. Now, in the canonical ensemble, And by the way, I should say, if you've ever gone through the derivation of this, the fact that the system is infinite and that you're in the grand canonical ensemble, summing over all possible particle numbers, in some sense, that makes this easier. I don't want to say easy, but easier, because it lets you do things which is hard to describe, but you have all of these infinite sums, and you can sort of break them up and put them back together in ways that you can't if the sums are finite. And the problem is that in the canonical ensemble, well, we work at fixed n. And if we work at fixed n and we want an exact result, if the volume is infinite, it's just an ideal gas. So we have to have a fixed volume as well to have a non-ideal gas. So we have to have fixed n and fixed volume. And this is actually harder as far as I can tell, unless, again, maybe I'm just that slow, but it seems a lot harder than the grand canonical case. And so I was reduced after shedding a lot of tears to looking at a very simplified example of two spheres in a small volume. Now, the smallest volume that you could look at is something which, so here my spheres, my rods have length 1. And the smallest volume I could look at is one that has about a length of 2 plus something. So 2 is the minimum that you need to hold the two spheres. And if you're going to get anything interesting, they have to be able to move a little bit. So you have 2 plus something. This is quite special.
Maybe if I interrupt for a second, Jim, excuse me. Let's shift the whole timetable 5 minutes into the past. So Jim has another 5 minutes, and that includes the discussion.
Okay, well, we're not going to have any discussion. I'm happy to answer questions offline or whatever you like. But anyways, let me just finish here. So thank you for telling me, Matthias. So this is quite a special case, it turns out. And the reason is because the centers of the spheres can never be in the same place. And what I mean by that is, of course, they can't overlap simultaneously. But the range available to the first sphere, the range over which it can move, and the range over which the other one can move do not overlap. So you have two sort of disjoint domains for the centers. And that turns out to be very special. So you can work out this case. The problem you end up with is the expressions are singular. And you sort of know that the singularities have to cancel, but there's no good way to control them, to know exactly how. And it turns out that in order to see that, you really have to go to a larger system and then take the limit that you get to this very restricted geometry. So what I ended up working out is a system where the length is 3 plus a little bit. In principle, you could hold 3 rods, but I'm only going to look at the case of 2. And here, there are still very special domains, and I guess I have to speed up because I'm going to run out of time. But anyways, you have a domain where you can only find the center of rod 1. You have an overlap domain where both can be, and then you have another domain where you can only find the center of rod 2. So what happens here? You can write down the partition function. That's quite easy. There's only 2 particles. You can work out the local density, and it divides naturally into 3 pieces corresponding to these 3 domains. Here, there's only 1 particle. Here, both particles give contributions, and here only the second particle. And if you look at this, there's a very strange but very useful relationship between the density in the very leftmost part of the space and the density in the very rightmost part of the space, plus 2 sigma. That means 5 sigma over 2 up to 5 sigma over 2 plus delta. And that's the very rightmost limit of this small space. So I don't really know why this has to be, but this relationship turns out to be very useful. So the only thing I know to do with something like this is to take derivatives and try and rescue this potential from under the integral. So you do that, and this is the cleanest way I can find to do that. It's still not terribly useful, but because here you have the potential at x, and here you have an x plus sigma, but it turns out to be more useful if you shift the arguments. So this is just a constant shift, so it doesn't change the expressions. And then you notice, you could notice the same thing here, but it's more, I get my results by looking here. You notice that some of these domains overlap. And so some of these expressions are valid in a small overlapping domain. and this can be exploited. And this is really the key to getting an exact result. So you can exploit this, and well, this is what I did for 2 months, and then you get this result. So this doesn't look very explicit, but it is. This is showing you the field as a functional of the density. And the space is split into a bunch of domains. So I'm not going to go through this in detail. I've put a paper on arXiv, which I guess will be there tomorrow, so you can see all the details there. But in the leftmost domain, you actually get a differential equation, which I don't know how to solve analytically. It involves the density and some of the other domains. That's not a problem. But you see it has this really weird structure. And as far as I know, there's no analytic solution. Then you get some analytic solutions, some analytic expressions in the majority of the space. And in the rightmost domain, you have this weird relationship. But one way of writing this relationship, if you use this, is it's just this equation rewritten with all of the, with a shift of x goes to x minus 2 sigma. But it's, anyways, as I say, this weird relationship is quite useful. And there's some quantity floating around here, which I've called lambda, and it looks like this. It's kind of a local packing fraction related to it. It becomes a local packing fraction in certain cases. And you can write down the exact partition function, and you can actually work out the Helmholtz functional, which is not anything very nice, but you can work it out. Now, what is interesting, and this is just about the end of my talk, is that as you take the limit as this delta, so remember the length of this volume was 3 spheres plus delta. If you take the limit as delta goes to 0, you get something for a small but not 0 delta. You get something that looks like this. This expression is exact up to order delta over sigma. And this looks weirdly like the usual grand canonical result. There's the ideal gas term, and there's something which you can write in terms of the local packing fraction and the scalar function. The only difference is that the domains are different. And unfortunately, I wish I had written this clearer, because you should write this expression for this particular domain. And then what you see is that the only difference is that the limits of these integrals, this integral in the grand canonical cases is 0 to 3 sigma plus delta, instead of being sigma to 2 sigma. So it's only in the limit of the integral that there's actually a difference. So that's something very strange when you think about this as being a very small system, and somehow, at least in a certain case, the functional looks the same as another one. You might think the only time this should happen is in the thermodynamic limits. So I don't understand this at all, but it's quite interesting. So this is the end of my talk. My message is very simple. DFT in the canonical.
I think we can read it, Jim. Yeah. Thanks very much. We have to stop due to time reasons, but maybe there's a question. Let's